Hi everyone, this is Andrea, and today we're going to be talking about simplifying and comparing fractions. This is the video that would go along with the beginning of the fraction unit. In particular, we're going to be talking about simplifying and comparing fractions today. So let's start out with this idea of factors. So what are factors? They are numbers that are multiplied together to create a product. And a product is just the answer, right? So we might take a look at the factors. Let's just say 2 times 3 because we know that they will give us a product of 6. We could also say that 1 times 6 is 6. So 1 and 6 are factors of 6, and 2 and 3 are factors of 6. Let's now look at this idea of factor pairs here. What we're really doing is just talking about this pair that goes together. 2 times 3, right? Those are pairs that when multiplied together make 6, and 1 and 6 would be also considered factor pairs. All right, so let's look at some examples of the type of problems that you guys will be asked to do. For example, you might be asked to find all the factors of a number. In this case, I just happened to pick 336. Well, we have a couple of different methods that we can use. One of the methods is just by simply listing the factor pairs, and we actually have a couple of ways that we can do that. In the beginning of this course, specifically in units 2 and 9, we ask that you don't use a calculator. So this technique or method can be a teeny bit tricky, but basically you can just go up, or you can just kind of list your factor pairs. We know that 1 times 36 will work, right? 336 is an even number, right? So we would have 2, and we would divide 336 into 2. Well, we could do that pretty easily. We can also just go over to the side and do this. You can also just do this kind of mentally. But we can also do our long division, right? I'll remember that. It's been a while. To do our subtraction. So 168, 2 times 168. We can see that this could go on for a while, right? 3 into 336. Well, that would be a 1 and a 1 and a 2. That's what we would call short division because we don't have any remainders, right? Oops, I think I must have messed up here. That is not right. 112, 2 times, oh yeah, that's right. Okay, 3 times 112. All right, so we can try 4. 4 into 336. 4 goes into 33 8 times, which would be 32, and 16. So of course we've got 4 times 84, and so forth. You guys can see that we start to look at these pairs, these factor pairs, and you can go up with your calculator if you want to. If you're doing this particular task, it's okay for you to pull out your calculator and just kind of get an idea. The other thing I wanted to mention to you is in the back of your book, of your workbook, you guys actually have a multiplication chart, and the multiplication chart would help you a lot. You can find the number 336 and just go up by, go to the side horizontally and vertically and see if you can find factor pairs that would go into 336. We know that 5 is not going to be a factor because 336 is an even number, and we know that 5, the only numbers that 5 go into would be numbers that end in a 5 or end in a 0, right? So we know that's not going to work. If I take my calculator out or look at the multiplication matrix for 6, I can see that 6 times 56 works. I'm just going to show you an example of another way to do the short division. Let's try 7. If you have just one digit out here, kind of like we did here, we don't necessarily need to do the long division. This is kind of just a little trick that we can do. 7 into 33 goes 4 times. I'm going to get rid of this up here so that we don't have as much going on. 4 times, which is 28. And from 28 to 33 is 5. So you can actually just put your 5 right here. And now it's 7 into 56. And we know that 7 goes into 56 8 times, right? So we don't even need to do the long division here. So we've got 7 times 48. So we could also do that with our 8. I'm going to go ahead and just do it on my calculator to make it a little quicker. 8 times 42. So I happen to pick a really long example here, but that's okay. 336 divided by 9 is a decimal. So we know that that does not work, okay? 10, of course, we know that anything that's divisible by 10 has to end in a 0, right? So we'll move up to 336 divided by 11, which is also a decimal. So that's not going to work. 336 divided by 12 does work. Oh my goodness. Okay, I need to put that back to my pen here. So 12 times 28. And you guys get the hint here. We're going to just kind of keep going until we close the gap between these numbers here. So 14, you can see 14 times 24. These two factor pairs are getting closer and closer together. And so we know that we're closing the gap there between those. And therefore we know we won't have any more options. 16 times 21. So that gap there is getting smaller and smaller. And let's try 18. That's also a decimal. 19. And 20 is not going to work. And I know that this number is 21. Now I know that what I'm saying there, just to illustrate the distance between these factor pairs, may not be quite as clear as if we were to do what I call the rainbow method. And I know it's kind of a little silly, but when I learned these way back long ago when the dinosaurs were roaming, we learned the rainbow method. And it is a little bit silly, but I kind of like it, because if we write our factor pairs basically like this, so we've got the ends of the rainbow basically, we know that these factor pairs here are connected, right? And we go up 2 times 168. Now there's no way I left myself enough room at all, but the idea is that as you go up, you start to write these down, and as you go up from this end, right, higher, and this end you go lower. Basically, when you get to the middle here, you're going to have the two factor pairs 16 and 21, and so you'll see that those ends, you know, there's really nothing left in the middle there. You can check 17 through 20 and make sure that they don't go into 336, but what you're doing is there's a visual way there of looking at whether or not you have any factors that you left out. Okay, so the idea here is that you can see that this can get a little bit lengthy depending on what number it is that you're having to find factors for. So there's another technique that we call prime factorization that is sometimes really handy. And you guys might have learned this back in school, and they might have referred to that as using the factor tree or factor trees. And what we do is we use a factor tree to write the product of the sum of the product, as a sum of prime numbers. And remember that prime numbers only have factors of 1 in themselves. So like 3 is a prime number. 1 times 3, those are the only factors of 3. 5 is a prime number, right? Only factors of 5 are 1 and 5. 2 is a prime number. So that's kind of what we're getting at there. And basically what we do is we write down our original, so our product, and we just create this tree with some limbs basically on here. Now the factor pairs that you write at the end of these limbs really don't matter as long as they're real factor pairs. So I could have used any of these factor pairs up here. I tend to like to start with 2 if I can, because it's already a prime number. When I get to a prime number, I stop. 168 is not, of course, we know that. But I can stop this branch here because 2 is already a prime number, right? And I can keep dividing this by 2. Half of 100 is 50. Half of 60 is 30, so that's 80. And then we have 84. Okay, so we're just going to kind of keep going. 2 is another, of course, prime number. And half of 80 is 40. Half of 4 is 2, so 2 times 42. From here, you can do whatever you want. You can keep going by 2s if you prefer. You can also just go to some basic math facts that you have. So I know that this is 6 times 7. I know 7 is prime. 6 is not, but 2 times 3 is. And they don't often teach to circle the prime numbers when you get to the end there, but I like that because I can kind of see what it makes, it makes it easier for me to see what all my prime numbers are. So what this is saying, guys, is that 336 is equal to 2 times 2 times 2 times 2 times 3 times 7. Let me make sure I've got this. 1, 2, 3. Yes, so there's 4 2s. We can see we got that. And then there's a 3 and a 7. And if we were to take our calculators and multiply 2 times 2 times 2 times 2 times 3 times 7, we would definitely get 336. And I would actually advise you to do that just to double check yourself. We usually are asked to write this in exponential form. Exponential form. And that is because it's kind of wasteful and just not as clean and concise to write 2 4 times. So we say 2 to the 4th. That's showing that we have 4 2s that we're multiplying together. And then times 3 times 7. Okay, so this would be the prime factorization of this original number 336 written in exponential form. And you guys are going to have a few other problems that you're going to practice with that. Make sure that you understand that process because that is going to come back around later on. And of course, if you need help, make sure you ask. For sure, we can definitely help you with that. Okay, let's move on to the idea of simplifying fractions. So a fraction is simplified when the numerator and the denominator have no common factors other than 1. How we simplify is dividing the numerator and the denominator by the GCF. And the GCF just stands for greatest common factor. Of course, greatest just means the largest, right? We're just looking for the largest number that goes into both the numerator and the denominator. So when we have fractions in simplified form, they can be proper fractions, where the numerator is smaller than the denominator. So, for example, 2/3. That would be considered a proper fraction. They could be an improper fraction. That's when the denominator is actually smaller than the numerator. So we would list 3/2, for example, as an improper fraction. And it used to be that improper fractions were not considered simplified. That has actually changed. Kind of that notion has changed. As long as there are no common factors left in your improper fraction, this can be left as a simplified fraction. You do not need to convert to a mixed number, unless, of course, it asks you to. So mixed number, of course, is a whole number and a fraction. So if we went ahead and converted this to a mixed number, we would say, okay, 2 goes into 3 one time. I have 1 left over. And so I would write it as 1 1/2. 1 1/2 is exactly the same as 3/2. And I did include some steps here, which is basically what we just did when we were looking kind of back and forth between these two fractions here. If we were converting from an improper, so right here, we just improper fraction down here to the mixed number, we divided the numerator by the denominator, right? So 3 divided by 2 is 1. right? So the quotient of 1 becomes our whole number. That's where we got this 1 here, right there, right? The remainder becomes the numerator. Well, we had 1 left over, so that's where this 1 comes from. And then we keep the same, or the original denominator. You notice the original denominator here is 2, so we just keep that same denominator. So going from the other direction, let's actually do that. So let's go from the other direction. Let's go from 1.5, right? And let's see how we get 3/2 from that. So in order to do that, we multiply the denominator by the whole number. And sometimes when you're first learning this, you can just put the little symbols in. That's what we're really doing. And we're kind of going this direction. We say 2 times 1 is 2, plus 1 is 3. And you write that as your numerator, okay? And then you just keep your same denominator, okay? So going from the improper is more of a division. Going from the mixed number to improper, you're doing a multiplication and an addition. I'm going to throw this out there right now. I know we're not yet dealing with negative numbers, but if we had a negative number, let's just say we're going to have -2.5, let's say. When you are converting negative mixed numbers to impropers, you will literally ignore this for now. Okay, you're going to ignore the negative sign. It's a very common mistake. So I'm going to bring it up now and I'll talk about it later as well. So we're still going to say 2 times 2 is 4, plus 1 is 5, right? And 5/2, and then this little negative sign comes over and it literally just gets stuck onto the front of that fraction. So ignore the negative sign until the very end. All right, so let's take a look at simplifying some of these fractions. So in example number 1, it asks us to simplify 48 over 126. Now, if we kind of remind ourselves how we do that is we're looking for this greatest common factor here. Now, sometimes we don't always know the greatest common factor, right? We would really want to divide by the greatest common factor over itself is really kind of what we're doing. Greatest common factor. A lot of times we don't know what that is. I mean, we can use our multiplication chart and we can try to find the greatest common factor, but the reality of this is that you can really start anywhere and just keep going. You can notice that both of these numbers are even numbers, right? So if we don't know the greatest common factor, we want to at least choose a common factor. So let's start with 2. Half of 48, well, half of 40 is 20, right? Half of 8 is 4, so that would be 24. And then that would be 50, 63. Okay, so half of 126 would be 63. All right, so we look at 24 and 63. We're looking for any other common factor. We know that 3 happens to go into 24. 3 definitely also goes into 63. 24 divided by 3 is 8. And 63 divided by 3 is 21. And we can search for a while, but we will find that 8 and 21 do not share any common factors, and therefore we are finished at this point. Now, interestingly enough, if we go back and we look and see what we divided by, all of the numbers that we divided by, and we multiply those together, that's going to give us that GCF. So the GCF in the end ended up being 6. So if we had divided 48 over 126 by 6 over 6, we would have gotten to the answer here quicker. But in reality, guys, it doesn't matter. It really doesn't matter. Okay, so let's take a look at example number 2. Now, if we are simplifying and we know that both of these end in a 0, we can mark that 0 off the end. That's basically the same as dividing both of these by 10, numerator and denominator, right? But you can just simply cross that out on the end. Now, you can't cross a 0 out in the middle with a 0 that's on the end. but you can cross these out. So what we have left here is 24/14. So we're going to look for a common factor here. I'm going to just stick with 2. It's going to give me 12/7. Now remember that I had told you that an improper fraction is considered simplified as long as there are no other common factors. So this would be simplified, right? Some students would have preferred, even from this point, to create a mixed number here. They'd say 14 goes into 24 one time, right? And then we have 10 left over. Okay, and then in this case, the fractional part is not fully reduced, right? The fraction part needs to be reduced. And we know that we can divide both of those by 2. So in the end, we would have 1 5/7, right? And we know both of these are the same because 12/7, if we were to write that as a mixed number, 7 goes into 12 one time, 5 left over, and 7 is the original denominator. So I would just suggest to read the directions, make sure that it's not asking you to leave your answer as a particular, either improper or mixed number, and then it's really your choice. I think the main idea here nowadays, the thinking is that when you're doing computation with fractions, most of the time you need them in improper form to do the computation, and so why change them to a mixed number if you have to change them back to do other computations? Because we get into multi-step problems where we're going to have to keep working. So I think that's one of the reasons why it's a lot more acceptable to leave your fractions as impropers. Okay, now sometimes it's, let's looking at example number 3, sometimes it's helpful to make everything an improper fraction from a mixed number before we do the simplification, but most of the time it's not. I mean, this is a whole number 6, and then we have this fractional part here. We do not need to take 27 times 6 plus 18 and make this humongous number, right? Because that's just wasting our time. So let's just look at the 18/27. We're going to look for common factors here, or the greatest common factor. Okay, we could start with 3. We know that 3 would go in. And we also know that 9 will go in, right? So we could immediately just cut to the chase and say, okay, well, this is the same then as 6 2/3, right? If we knew that, we could get right to the point. If we didn't know that, that's okay. We would take it a little bit slower. We would take our 6 and 18/27, divide by 3, which I'm just going to carry this down to the end. We can just drop that whole number for right now. It's going to be 6 and 9, right? But we got to keep on going. 2 and 3. So we just bring these two pieces down and put them back together. So it doesn't really matter. If you know the GCF right off the top, great. If you don't, just find a common factor and just keep working at it. Okay, guys, now next is this idea of equivalent fractions. Let's try to get this a little bit bigger here. So equivalent fractions, the idea here is that we have fractions that are actually different numbers, but same value. And we can just show an example of that. If we had, for example, 4/8, 4/8, we can also show that as 1/2. In fact, we know if we reduced that, we would get 1/2. Well, 4/8 and 1/2 are considered equivalent fractions. They represent the same value. We can show that if we wanted to kind of look at this pictorially. We know that fractions represent parts of a whole, right? And so if I were to draw 2 circles, now these are actually supposed to be, actually let me do this here. These are actually supposed to be the same exact size. Sorry, Gab, can't talk right now. But so it's kind of close. Not the best, but I'm doing my best here. And in this circle, we know that we need 8 total parts, right? And we know that 4 of them are colored or shaded, right? And in this particular example, we've got a circle, should be the same size, but it's cut into 2 pieces and only 1 part is shaded. You guys can see that we still have the same value in terms of the shaded part. It's just that we have a different number of pieces, right? That's the whole idea behind equivalent fractions. Okay, so when we're searching for equivalent fractions, we have a few different methods that we can try. Change colors here. So we have several methods. One is let's just try reducing the fractions down to see if they're the same when you're all finished, kind of like we have up here. Another idea is to use this idea of a common multiplier or divider if needed, which means we're looking for a connection between the two, right? So if I were to go back here and I'm looking for a connection here between the two, I can see, oh, well, there is a common, actually, if I went from right to left, it's a common multiplier of 4. But if I go from left to right, I'm dividing by 4, which means I have to do the same on top. Otherwise, I'm changing the value if I don't do the same top and bottom. But you can see that totally works, right? So that's this idea of common multiplier. And finally, we have cross products. And cross products is actually going to be pretty important. Later on in the quarter, we're going to be we're talking about proportions, and we're going to be using cross products with our algebra. And cross products, basically, if I took those same 2 fractions that we had above, and we wanted to really see whether they are the same, we basically are just using this idea of going diagonally or across. And we're saying, oh, okay, so 4 times 2 is equal to 8. And 8 times 1 is also equal to 8. So when you cross multiply, those products need to be the same. That's the idea behind cross products. Okay, so we have this example problem here. It's asking us to determine whether 2/3 and 40/60 are equivalent. So let's just try the first method here where we're going to reduce the fractions down. Okay, well, 2/3 is already in reduced form, isn't it? And then we have 40/60. So if we start to try to reduce that, we know the ends can go off. That's like dividing by 10. Then we have 4/6. And that's not quite done yet. We know we have a common factor here of 2, right? And that's going to give us 2/3. So in the end, we can see 2/3 is definitely equal to 2/3. So we have proven, yes, these are definitely equivalent fractions. And we use the idea of just reducing those fractions down in order to prove that. All right, let's try this idea of using the common multiplier. All right, so let's write these in here again. So we've got 2/3, and we have 40/60. Let's see if these are equal. So we're going to go this direction, and we say 3 times 20 gives us 60. And so 2 times 20 better equal 40. If it doesn't, these are not equivalent, but indeed they are. All right, so we're just looking for a common multiplier or divider. And lastly, let's use this idea of our cross products. So we've got 2/3 again equals 40/60. Okay, and let's just go across. So 2 times 60 is 120. And we've got 3 times 40, which is also 120. So we've checked it out. We've proven, yes, these indeed are equivalent fractions. And we just used 3 different methods to figure that out. Okay, so, and you guys, I would say that the method changes all the time depending on the problems that you have. Sometimes there is not a common multiplier. Your common multiplier or divider is going to be a decimal, right? For example, let's say that we had, I don't know, 49 over here instead of a 60. Well, 3 doesn't go into 49 evenly, right? So it'd be really hard to use this method, right? So you're going to try different methods to kind of figure out your equivalent fractions based on what you're given. Okay, and the last concept that I wanted to talk about here is this idea of comparing fractions. And in order to compare fractions, we're using the greater than sign right here or the less than sign. Okay, greater than sign, there's all kinds of different ways that are being taught. I think I taught this is an alligator with his mouth open. He wants to eat more. I've heard like Cookie Monster, that sort of thing. But in essence, what we're really doing is we're saying that, for example, 10 is greater than 8, right? So the sign, if we're reading it left to right, the mouth is open toward the larger number. We could actually read this from right to left, and this would actually say 8 is less than 10, right? 8 is less than 10. So we can read it left to right or right to left, but the bottom line is that the open mouth, the greater than, is going to be facing the larger number, right? And that's true over here too, right? You can see that. Or you can kind of think of it as the opposite, that the less than sign is always pointing to the smaller number. Okay, however you want to look at that. Sometimes those get confused, so just kind of want to point out a couple of strategies. Okay, guys, so when we're comparing two different fractions or more than two fractions, sometimes we're asked to compare lots of fractions, we can estimate by reducing the fraction and observing, but that's not always accurate. Okay, we can do an estimate, but a lot of times it's not really proving it. In order to prove it, we have to find common denominators. So in other words, those circle graphs that we did down below, we have to make sure that both of the pies, so to speak, are cut into exactly the same pieces, because if we have that, then we know which fraction is bigger, because some of them are slightly bigger, but it's really hard to tell if we're just estimating. So in order to prove and find our common denominators, we need to go through the steps for finding a common denominator. So what we're really doing is we're looking for the least common denominator, or the LCD. Okay, and in order to do that, the first step is to find the least common multiple of all numbers. Okay, and then rename those fractions using that common multiple. Okay, so that they both have the same number in their denominator. Let's take a look at our example here. We've got a 3 in the denominator and an 8. We've got 2/3, and we're trying to figure out whether 2/3 is greater than or less than 7/8. Well, we can do an estimate here, but we don't know for sure, okay? If we were asked to do the comparison, we would want to show proof. Okay, so that's kind of what I'm getting at, is we want to show the steps. We want to show that we know that for sure, and we want to show that we know how to show that using our math, using our algebra. Okay, so what we're really doing here is we're looking for the least common multiple. And basically what that means, guys, is of course you can just multiply these two numbers together and we'll get a 24, of course, but sometimes you have huge numbers. Maybe your denominator is 33 and 812 or something. I mean, that's just huge. And so you're going to get these large numbers. One strategy is to write multiples of the largest number. So I would write 8, right? And the second multiple, so that's really 8 times 1 is 8. 8 times 2 is 16. 24, right? 32. This is what we mean by multiples, which is go up. And what we're looking for then is which multiple What's the lowest multiple or the least multiple that 3 goes into? It doesn't go into 8, doesn't go into 16, but it does go into 24. Okay, so we can write the denominators now as 24, right? We changed our denominators. Okay, but what did we change them by? We can't just randomly change denominators, right? The common multiplier here that we used in the first fraction is 8. 3 times 8 is 24. And of course, I can't change the denominator without changing the numerator. I want to point out to you that 8 over 8 is just a very fancy way of writing 1. 8 over 8 is just equal to 1. So we can use this idea of a multiplier over itself to get what we need, right? So this is going to give us a new numerator of 16. And of course, we didn't multiply 8 by 8. That would give us 64. We multiplied that by 3. So we're going to be doing the same here, right? So now we can easily see which fraction is bigger. Here we have 16 out of 24, and here we have 21 out of 24. So the second fraction is larger. So we're going to put a less than sign here. Okay. So use this idea of finding least common denominators when you're comparing those fractions rather than using an estimate. I mean, it's always good, I think it's good critical thinking to look at it and try to guess or estimate what you're going to get. But it's always good to also know the steps to make sure that you can prove it. Okay, guys, so you're going to have quite a few problems on your worksheet like this. Just refer back to this if needed. And we will be